Hello everyone. In this video, we're going to evaluate type 1 improper integrals. So here, we're going to consider integrals over an infinite interval like negative infinity to 2, 5 to infinity, and negative infinity to infinity. And we consider here integrands that are continuous on the given infinite interval. We're going to determine as well whether each of these improper integral is convergent or divergent, and interpret the values of these integrals in terms of areas. Let's get started. Let us evaluate this improper integral here. So the first step here is to write this improper integral as a limit, and we can write it as limit as t approaches negative infinity of this one. So we can write this as the limit of this proper integral from t to 2 as t approaches negative infinity. Now, let us evaluate this integral here. So we can easily evaluate this by substitution. So we can write here the denominator as the square of x squared, and then this constant here is the square of 4. And then if you think of this as our u, then the du is just equal to 2x dx. So this will be our du. So therefore, we can easily evaluate this integral using this formula here. Integral of du over u squared plus a squared is equal to 1 over a tangent inverse of u over a plus c, where a is greater than 0. But of course, don't forget to multiply this integral here by 1/2 because the original integral has x in the numerator, not 2x. And now using this formula here, so just think of this as integral of du over u squared plus a squared. We'll get the antiderivative 1 over a tangent inverse of u, which is equal to x squared, over a, which is equal to 4. And then, of course, times 1/2, and then evaluated from t to 2. So here we plug in the upper limit first. We plug in the 2. So we'll get here 2 squared over 4, so that is equal to 1. And then we plug in the t for x, we'll get here 1 over 8 tangent inverse of t squared over 4. Now, we know already what the tangent inverse of 1 is. It is just equal to pi over 4. Now, how about tangent inverse of t squared over 4 as t approaches negative infinity? So as t approaches negative infinity, this expression here approaches positive infinity. So what happens to tangent inverse as the input approaches infinity? If we go back to the graph of tangent inverse, so the tangent inverse looks like a cube root function, but it has horizontal asymptotes, y equals pi over 2 and y equals negative pi over 2. So the graph looks something like this. So as the input increases without bound, so as you can see, the points here are getting closer and closer to the line y equals pi over 2. So therefore, the value of tangent inverse of t squared over 4 is approaching pi over 2. Therefore, the value of our indefinite integral is equal to this difference, which is equal to negative pi over 32. So because this limit here exists and it's equal to this negative pi over 32, we say that this improper integral is convergent. Now, how do we interpret this value geometrically of this improper integral? If we look at the graph of this integrand here, we'll get the following. And if we consider the graph over the interval negative infinity to 2, so we have this region that is bounded above by the function, and then this region bounded below by the function. So we can interpret this value here same as for definite integrals. This negative value here means that this blue region has a greater area than this pink region. So the area of this blue region here is pi over 32 more than the area of this pink region here. That's the reason why the value of this improper integral is negative, which is equal to negative pi over 32. Let's move to our next improper integral. So let's evaluate this one. So here again, our integrand is continuous on the interval 5 to infinity. Again, the first step here is to write it as a limit. So limit of this integral from 5 to t as t approaches infinity. And why did I write our integrand in this form? Because it looks like this can be evaluated by u-substitution. So if we think of this one to be our u, then this is just our du. So this is just integral of u squared du. So we can easily find an antiderivative for that one, and we'll get here. So if this is our u, this is our du. So integral of u squared du is u cubed. So this is your u cubed over 3. And then evaluating this first at x equals t, we'll get this one. And then minus at x equals 5, we'll get the following. Now, as t approaches infinity, we know that this ln t here goes to infinity. So this term here goes to infinity. And then this is just a constant. So this difference here goes to infinity as t approaches infinity. So because this limit here is infinite, we say that the improper integral is divergent. Now, geometrically, what does this value mean? So it means that if we look at the graph of our integrand, so the graph here, so that is greater than 0, okay, for x greater than or equal to 5, it only tells us that this area here, okay, as x approaches infinity, is infinite. So this region here doesn't have a finite area. Now let's move to our third and last example. So let's evaluate this improper integral from negative infinity to infinity of x e to the negative x dx. So this integral can be written as sum of these two improper integrals. Now, when do we say that this original improper integral is convergent? This is convergent if these two improper integrals are both convergent. But if one of them diverges, then this original improper integral is divergent. Now, let's try to evaluate the second improper integral first. So here we can write that second improper integral in limit form this way. Again, you have your upper limit which is equal to t and t approaches infinity. And this form of integral looks familiar. So we can evaluate this by integration by parts. And we can use tabular form to evaluate these integrals. If we use tabular form of integration by parts, so we have here the x, okay? So under the derivative column and then e to the negative x under integral column. So we differentiate it, okay? Twice, we'll get here 1 and then 0. And then we find an antiderivative of this, negative e to the negative x. Again, antiderivative e to the negative x. So we'll get an antiderivative here of x e to the negative x, which is equal to, so we have this product here. So x times negative e to the negative x. And then minus this product here, which is e to the negative x. So plugging in t first, we'll get this expression here, and then minus, when we plug in 0, we'll get here 0, and then minus 1, so that is negative 1. Now, we know already that as t approaches infinity, e raised to negative t approaches 0. So that is just 1 over e raised to t. Now, what is the limit of this term here as t approaches infinity? So note that this term here can be written as negative t over e to the t. And as t approaches infinity, so this has an indeterminate form infinity over infinity. Of course, the numerator goes to negative infinity, but we say that that is of type infinity over infinity. Okay, so this limit form negative infinity over infinity is of type infinity over infinity. So by applying L'Hopital's rule, we'll get here limit of the derivative of the numerator, which is negative 1, derivative of the denominator, which is the exact same thing. And clearly, the limit as t approaches infinity is equal to 0. Therefore, the limit of this expression here is 0 minus 0 plus 1, which is equal to 1. So this tells us that this improper integral here is convergent. Now, the convergence of this integral here is not sufficient to conclude that this original improper integral is convergent. So we have to show that this is convergent as well. Because if otherwise, then this original improper integral is divergent. So let's evaluate this improper integral here. So again, the first step here is to write it as a limit. So we have here the lower limit t, and this t approaches negative infinity. And we know already an antiderivative of this one. So same as before, we have here negative x e to the negative x minus e to the negative x. So we plug in 0 for x first, and we'll get negative 1. And then plugging in t for x, we'll get here plus t e raised to negative t, and then plus e raised to negative t. Now, this sum here can be written as e raised to negative t times the quantity t plus 1. And as t approaches negative infinity, so this is like e raised to infinity, which is a huge number. And then t plus 1, so that is a huge negative number. Okay, so a huge positive number times a huge negative number. It will give you a huge negative number. So even if you add that to negative 1, you still get a huge negative number. So the limit here is equal to negative infinity. And what does this tell us? It tells us that this integral here is divergent. And because this is divergent, we can now conclude that the original integral is divergent. So here, if we have computed for the value of this improper integral first, then we don't need to evaluate this improper integral, because after you show that this is already divergent, you can actually conclude already that the original integral is divergent. Now, because we have shown that this first integral here is equal to negative infinity, and this second integral is equal to 1. So clearly, the value of that original improper integral is equal to negative infinity, and therefore it is divergent. Now, how do we interpret this negative infinity geometrically? If we look at the graph of our integrand, so this is the graph of our integrand, x e to the negative x, and we have here the regions bounded by the function and the x-axis. Again, we are considering here the region bounded from negative infinity to positive infinity. So this region here extends indefinitely to the left and extends indefinitely to the right. So our computation tell us that the area of this pink region here is equal to 1. So if that area is equal to A, the value of A is equal to 1. And the area of this region here green region is equal to infinity. Again, this area B denotes the area over the interval negative infinity to 0. So this area is infinite. So the value of this improper integral is negative infinity, which is equal to negative of b. Therefore, the value of this improper integral from negative infinity to infinity of our f of x, which is x e to the negative x dx, is equal to negative infinity. And of course, we got this negative infinity as like area above, which is 1, minus area below. Okay, so that is minus b. So which represents net area. And this is also how we interpreted the value of a definite integral.